So we have up to this point really focused on how the human body interacts with foods. What I want to start to talk about now is why do we do what we do to foods? Why do we do the chemistry? Why do we do the different unit operations that we do? So for the next month, we're going to talk in depth about the chemistry and design of foods. And we're going to do this by dealing with the macronutrients individually. So we're going to go through 3+1 topics. We're going to talk about water chemistry, lipid chemistry, carbohydrate chemistry, and protein chemistry. And we're going to continually tie that back into the relationship to do with diet. So today, we're going to start with water. And water is absolutely a remarkable molecule. Without water, make no mistake about it, there could be no existence of life on Earth. So when we talk about water, the first thing we have to understand is the scarcity of water and the importance of water. In North America, we take for granted our water supply. Bear in mind that 770 million people are without access to clean water. This goes beyond just water that you drink. This goes also and speaks to water used in agriculture, water used in food processing, and water used in bathing and cleaning. So unsafe water kills 200 children a day. And 80% of the virus, bacteria-related diseases in developing countries are directly associated with waterborne infections. So water is an extremely important, scarce resource. If you don't think that water scarcity and quality is important in North America, you are gravely mistaken. And I'm going to illustrate it with 2 points. The first being Flint, Michigan. Does anyone know what happened in Flint, Michigan, or what is happening in Flint, Michigan? Yeah.
They haven't had clean water for 10 years or something.
It's not quite been that long, but it's been a long time. Does anyone know what it's contaminated with? Lead. And the problem with that is, once lead is contaminated in water, that whole reservoir that they pull from is contaminated. So there's no quick solution. Where are there major issues with water quality in Canada? Yes?
Like the northern parts?
Northern parts, specifically?
Like
Reserves.
reserves?
So reserves in Canada, it's a really weird legislative problem because it falls under the jurisdiction of the federal government, and the federal government does not supply sufficient funds to do water purification and water treatment on reserves, in part because the areas are so they're not densely populated. So the revenue that it would generate to put in these water treatment facilities, there's just such an imbalance that they won't build water treatment facilities. So if you go up into Northern Ontario into reserves, almost always, I would say years on end, they have boil water advisories. And often is the case when the water is not even palatable, meaning you can't consume it even under a boil water advisory. So don't take for granted the water system that we have in southwestern Ontario. Globally, it is atypical. So we're not going to watch this video. You can watch it later if you want. So when we talk about water, we typically require anywhere between 1.5 and 2.5 liters a day, depending on a couple variables. One is the amount of physical activity that you're undergoing, also dependent on your diet. For young people, dependent on the amount of alcohol you consume. It also depends on the weather and the temperature. So if it's a hot day outside, or if it's a very dry day, our skin undergoes a lot of desiccation and we lose a lot of water through evaporation. We also use water to produce urine to filter out any of the toxins in our body. So of those 2.5 liters per day, we drink about 1.5 liters. About a liter of that comes from food, the foods we consume, and the rest comes from metabolic reactions where there's a cleavage of molecules or a combination of molecules and that release of water. Now, without water, you will die in about 4 days. Compare that with oxygen, about 4 minutes. Compare that with food, a couple of months. Now, the human body is made up of 60% water. This is important to have turgor within your cells, so that rigidity. We also use water to produce skeletal muscles. It's also the major constituent of blood. So when we talk about transporting nutrients, either glucose, salt, or any bioactive that's water soluble, we require water to move those nutrients through the body. We also need to have an osmotic gradient between cells, the lymphatic system, and the circulatory system. So we have a driving force for water to actually move. So we require a certain amount of salt in that product. So again, we use water mainly to produce urine. Again, that's the kidneys are using it to filter out any of the protein, any of the urea and excess salts. So if we have a diet very, very high in protein, it's important that if you're lifting weights and taking a high protein diet, that you also consume extra amounts of water, because you have extra urea that you have to secrete out. And again, when we talk about the effects of urea and salts, we have to account for that osmotic gradient that's associated with solutes being in water, which we'll talk about. So an osmotic gradient is any time you have an imbalance across a semi-permeable membrane between two solute concentrations. So if you have a solute high in concentration on one side of a semi-permeable membrane and a solution low in solutes on the other side, water will diffuse from the low solute concentration to dilute the high solute concentration. So we'll actually see across the semi-permeable membrane, we will actually see a change in the volume associated with that second side. Again, it's because water is migrating across that semi-permeable membrane, and it's diluting that solute so that the concentrations on both sides of that membrane is in balance. Right? So this is one of the reasons we have to be careful with the amount of sodium and potassium and ions we consume. Because if our osmotic gradient gets too out of whack, we can lead to things like dehydration. If we're too low of concentration, so cells can actually begin to push water into the extracellular space to try to dilute that concentrated solute effect. And if we over-dilute it, we have problems. And if we over-concentrate it, we have problems. The other thing we have to think about when we talk about water is, again, water is not just something we drink. It's not just a constituent of beverages. It is essential in the production of all foods, irrespective of what food that is. The water cost associated with making new foods is dependent on the food itself. So you can see a pound of beef takes about 800 gallons of water to produce. To produce a gallon of wine requires about 1,000 gallons of water. A 0.3 gram burger, so this isn't a hamburger, we're going to talk about this in a minute, but that's about 0.3 grams. This requires 600 gallons of water to produce if it was beef. This isn't beef, we'll talk about it in a couple minutes. So water is not only essential to drink, but it's also essential in the formation of agricultural products. And remember that the quality of water, if it's portable water or not, is extremely important in the development or production of all agricultural commodities. Beef, but also it is associated with the foodborne outbreaks that we talked about with different produce. So we can have the internalization of pathogens if that pathogen contaminates the water supply. Now, this is where I get good at the course. So up until now, I've been outside of my forte. I am a chemist by training. So we're going to talk about the chemistry of this molecule. And this molecule, again, is extremely, extremely remarkable. Water can dissolve more compounds than any other solvent. Why is this important? Why does it matter if water can solubilize a compound? Why would that be important in nutrition? Yeah?
Because more of it is transported.
Right. So if we didn't have water as our primary transport system, our blood, we wouldn't be able to transport all the minerals, all the salts we consume, all the different bioactives, sugar, all of these things that move through our bodies, enzymes, so proteins, they all require water to transport that molecule or those molecules through the circulatory system. The other thing that's remarkable about water is it is one of the only molecules that when it freezes, it's less dense than the liquid component. So ice is less dense than water. Now, if this wasn't the case, our oceans would all freeze. We would not have life on Earth as it is today if water, when it froze, became more dense. Now, from a food processing perspective, why is that important? So who's going to cryogenically preserve themselves when they die? Who wants to cut off their head, put it in a vat of liquid nitrogen, and wait for science and technology to catch up so you can rebirth in some new form? Who, when they have kids, is going to freeze their stem cells? One person only? Two? Wow. Yeah, I bet most of you probably haven't thought about it yet. But when you freeze a food, and when you pull it out of the freezer, what do you notice? Think meat, a nice quality cut of steak. You buy your T-bone steak, you decide you're not going to have it tonight, you throw it in the freezer, a month later you pull it out, you're going to have it then. What happens, what do you notice about that steak? Yeah. So freezer burnt, I think you're right, but freezer burnt means something very specific. So we'll talk about that in a minute. But what do you observe? Yeah.
It changes color.
It can change color? Crystals? Okay, so it swells. So when you take it out and you thaw it, what do you notice? What do they always put under a piece of meat? That piece of absorbent material? That's to deal with drip loss, right? That's to do with exudate or water that's synericing out of that matrix. Why does that happen? Because as that ice freezes, again, it's less dense. Because it's less dense, it must expand. And that expansion causes disruption of cells. So cells rupture. It disrupts intermolecular interactions that hold cells together. So the intercellular material can begin to flow. So we end up getting exudates. We get freezer burn, which causes damage to the tissues. Another really interesting observation with water is if you add certain salts, so if you add sodium chloride to water, the volume of the water decreases. Again, it's remarkable that you're adding mass and the volume is decreasing. Why does that happen? So we'll talk about that in a couple minutes. Something else that we take for granted all the time is water boils at 100 degrees Celsius. If you take similarly sized molecules, we'll talk about methane. Methane is in what form at room temperature? Gas. So if water, with almost the same molecular weight, had a similar boiling point, imagine what would be happening to our bodies right now. We would literally be transforming into a gaseous phase. So the fact that water doesn't boil until 100 degrees Celsius means that we can have it as a liquid state on Earth, but as well in our body. And it has an extremely high surface tension. So if I take a drop of water and I drop it onto the surface of this desk, it'll form a nice meniscus, right? So in first year or in high school, you should have done some laser experiments, hopefully, where you take like a light pointer, you shine it through a light, you look at the refractive index, you look at the surface of curvature of that water. That's important for how water hydrates a food. So in the morning, if you want to make an instant coffee, right? Or if you're going to wake up in the morning and have a shower, you want that water to have a low surface tension, right? You want it to be able to interact with your skin or with that coffee matrix so it can hydrate. So temperature changes the surface tension of water molecules, thereby changing how it interacts with its environment. So how many of you take a cold shower versus a hot shower? Who are cold shower people? Anyone? Two? How many people are hot water? Yeah. Why do you use hot water? It feels nice, sure. There's another reason you want to use hot water. Hot water has a lower surface tension, therefore it wets your skin better, and your skin is not perfectly smooth, right? It's got crevices and creases. The older you get, the more pronounced they become. So if you're trying to remove fat and oils and dirt from your skin, you want to have a really low surface tension. You want to use hot water to clean. So if you're having a cold shower, you're not as clean as you would be if you had a hot shower. And this all comes because of first-year chemistry. So who remembers this column in the periodic table? Column 14. So when we talk about carbon, so carbon and oxygen are the two neatest molecules that there are, in my opinion. Carbon contains 4 valence electrons, right? Everyone remembers this. So everything in that column has 4 valence carbons. So what does that mean? If we go back to first-year chemistry, we have our 2s, our 1s orbital filled, our 2s orbital filled, and then we have 2 electrons in the p orbitals, right? Now, that doesn't actually happen, right? What happens instead? Have you all blocked out first-year chemistry already? That was my favorite course. I had the most wonderful professor for that. So, sp3 hybrid, right? sp3 hybridization. So the 2 electrons in the 2s orbital, one of those jumps up into that third empty p valence. So we actually end up with this sp3 hybrid where we have, instead of just 2 valence electrons, we have 4 valence electrons. Everyone remember that from first year? So that sp3 hybridization is what gives water its uniqueness. So in the case of methane, we have a carbon, and then we have 4 hydrogens, and those 4 hydrogens are covalently linked because of that sp3 hybridization. And we get a molecule that looks like this. Now, that color distribution, you see how there's a little bit of yellow and it kind of moves to green? That's what we call the dipole moment associated with that molecule. So in orbital theory, we have these orbitals, and those electrons are moving at an extremely high speed around those neutrons and protons, right? As those electrons move, they create very weak dipole moments, right? Those electrons are not static. So as those electrons move around that molecule, they create a little tiny electric dipole moment. What non-covalent interaction does that give rise to? When we talk about methane, what non-covalent interaction causes methane to interact with itself? So what are the main non-covalent interactions?
Van der Waals.
Van der Waals is the right one. So it's Van der Waals interactions. London dispersion forces, right? What are the other ones? Hydrogen bonding. Dipole moment. So when we talk about methane and having 4 valence electrons, those 4 valence electrons are able to interact with the 1 valence electron in hydrogen, so it can form 4 covalent bonds with 4 different hydrogen atoms. When it does that, when it does that, we get a very uniform molecule that has a uniform distribution of its dipole moment. So when we talk about molecules that only are able to interact by Van der Waals interactions, they can only interact with organic solvents. Things like chloroform, benzene, toluene. These are the primary constituents of what macronutrient? So when we talk about Van der Waals interactions, they play a very important role in lipids, fats and oils, because of that long aliphatic chain. Now, when we move over to 2 rows to find oxygen, we now have 2 more electrons. So we still have the sp3 hybridization that we saw in the water molecule, but now we have to add 2 electrons. We add those 2 electrons, and now we have two spots where we can have covalent interactions. Those other two electrons that were free in the carbon are now forming an electron pair with the extra two electrons that are associated with oxygen. So now we only have two spots for a covalent bond to happen. So when we talk about oxygen, now we have two hydrogens, not four hydrogens, that are capable of interacting with that oxygen molecule. What does that do? That creates a molecule with an extremely large dipole moment. What does that mean? It means that we have a positively charged end associated with the side that the hydrogens are on, and we have a negatively charged end associated with where the oxygen is. Does that make sense? So this dipole moment creates this electronic gradient, which then allows for what type of interaction? So how does water interact with itself? Through hydrogen bonding. And the strength of hydrogen bonding is about 2 orders of magnitude greater than van der Waals interactions. So when we talk about methane, methane needs very little energy to go from the liquid state to the gaseous state, because all we have to disrupt is the van der Waals interactions of those temporary, very weak dipole moments. When we talk about water, there is that permanent dipole moment which allows that to form a hydrogen bond. And when it forms a hydrogen bond, those bonds are extremely strong and require a lot of energy to break. Therefore, there's a lot of energy associated with the phase transition going from a liquid to a gas, or the latent heat of vaporization is extremely high. So because of this dipole moment, when we talk about methane, that molecule forms a nice tetrahedral structure. Remember from first year chemistry, a tetrahedral structure has that nice bond angle of 109.5 between every hydrogen. When you put those two free pairs of electrons, we get an electrostatic repulsion. So we have this large negative cloud that pushes down the hydrogens, which then causes a deviation from that 109.5 and drops it down to about 104.5. Now that dipole moment, we can see, changes the intermolecular interactions that we observe in van der Waals from about 0.4 kilojoules per mole up to about 30 kilojoules per mole. So again, the amount of energy that it takes to cause or to stop water from interacting with adjacent water molecules is about 100-fold greater than we observe when we observe van der Waals interactions. This leads to a much higher melting temperature. This leads to a much higher boiling point. It also leads to a higher specific heat capacity. The specific heat capacity is the amount of energy that's required to increase the temperature of that water by 1 degree Celsius. So how much energy it takes to heat up 1 kilogram of water by 1 degree Celsius. So if we look at food constituents, the highest specific heat is water. It takes the most amount of energy to elevate the temperature. We also have an extremely high latent heat of vaporization. This is why we use steam as a heating mechanism, because a lot of energy is carried in that steam, and when it condenses, it releases energy. So we can use steam as a very, very effective heating medium in the food industry. It's why when we talk about pasteurization, we talk about using steam. Now, what's interesting about water is, again, we aren't having the tetrahedral structure on a molecular level. We have the bent configuration, which again shows that deviation of bond angle from 109.5 to 104.5, right? Because of that large electron cloud. Now, because that molecule has a dipole moment, meaning it has a positive charge around the hydrogens and a negative charge around the oxygens. So when I come in close proximity to another molecule, my negative charge aligns with that adjacent water molecule's positive charge. The positive charge of that molecule interacts with the negative charge of another molecule. So what we actually see in water, something we call often amorphous or it lacks structure, actually has a ton of structure. And that structure on a supramolecular level, so not on a molecular level, again, that's the bent structure, but on a supramolecular level, forms these tetrahedral clathrates. So again, there's this supramolecular structure of water where each water molecule is able to interact with its adjacent water molecule by aligning its dipole moment so that that net dipole moment is uncharged. Does that make sense? Now, imagine for a second you take water, you have water, and now you mix oil. So now you have an aqueous phase, and in this aqueous phase we have a balance of the dipole moment because we have those molecules that can align and neutralize out that charge. But when it comes to the interface between a fat, let's say, so an oil droplet, a salad dressing, mayo, butter, lard, the human body, anything that has fat and oil, we have this interface that has these unbalanced hydrogen bonds interacting with molecules that can only interact by van der Waals interactions. So they're not happy together, right? So what happens? They minimize their surface area. When something minimizes its surface area, what shape does it adapt? Always, without exception? Sorry? A sphere. A spherical object has the greatest volume to surface area ratio of all shapes. So when you blow a bubble with your little soap, it's minimizing the surface area to minimize the surface tension between the air and that water phase. So water always has to balance these unbalanced forces of the water molecule. So when you begin to add oil, you have to add other molecules to balance this dipole moment at the interface, or else we have high surface tension and eventually separation. So why does this matter? Literally, life on Earth would not exist if it weren't for this unique structure of water. One, in most areas that are above 25 degrees Celsius, which is most of the world for part of the year, we would be in a gaseous state. So all of the reservoirs, all of the 60% of the water that makes up your human body would turn to gas. Not conducive to life. In food science, it's important because it structures foods. When you talk about the quality of a steak, or the hardness of a cracker, or dried pasta, or your instant coffee in the morning, it doesn't matter what it is. It relies on this unique structure of water, not only from a food preservation processing standpoint, but also from a structural attribute. So when you bite that cracker, that crispiness is associated with the state in which water is in that food. When we talk about the high latent heat, so the amount of energy that it gives off when it converts from a liquid to a gas. Think about on a hot summer day. How do you cool yourself off? You respire, you sweat, a dog pants. It relies on that evaporation of water from the surface of your skin. Because it has a high latent heat, it allows that, whatever material is, the human body, a plant, a crop that you're growing, to cool down. So you spray water on yourself when you're hot, that water evaporates, you cool down, you lower your body temperature. It's also why we use steam as a heating medium in food, because there's so much energy that's available to be given off by that food that it can begin to be used as a cooking medium. And again, from a nutrition perspective, we can talk about how it cools the body. When we talk about adhesion and cohesion, so how it interacts with itself, adhesion, how it interacts with foreign molecules, so lipids, cohesion. Think about if you're applying a pesticide to the surface of a leaf. If you have a hydrophobic medium and you spray it on the surface of a leaf, rain comes, it will wash it away. So you put a pesticide on, your storm comes, it washes it away. So you have to engineer your pesticides, your herbicides, whatever agricultural resource you're spraying on your crop, it has to be very carefully formulated so that it has a surface tension that will actually reside or adhere to that surface of the leaf. In food science, gels, meat, which we're going to talk about in a second. All of these things play a very, very important role in the structure of foods. When we talk about global warming, it's not really the temperature of the world that's going to be our downfall. It's going to be the loss in temperature gradients. Why does that matter? Well, all of the ocean currents, the whole reason our equator doesn't get to really high temperatures is because there's a temperature difference, and associated with that temperature difference is a change in the density of water. Remember, when ice freezes, density goes down. Water has its greatest density at 4 degrees Celsius. When water hits 4 degrees Celsius in the Arctic, it sinks and it forms the Atlantic jet stream. It goes across the equator, warms up, comes back across, and that whole cycle, all those ocean currents develop because of the density gradient associated with the dipole moment of water. So remember, when we talk about cohesion, adhesion, the high latent heat, the high boiling point, this is all because of the tetrahedral supramolecular structure, which arises because of the bent configuration and dipole moment associated on a molecular level with water. Now, why does this matter? Okay, what time is it? I'm just cognizant of time because we got something coming in a couple minutes. 4 minutes, okay. I'm going to start this. So we're going to take a quick aside here. Why isn't it turning on? Okay, pan is on. Okay. Just give me 1 second. Go live. I'm going to pull this off for a second. I broke it. So when we talk about meat analogs, so what is a meat analog? Anyone know? Anyone know what a meat analog is? Nobody knows. Come on. Veggie burgers? Meat analogs are plant-based meats. So when we talk about So when we talk about animal-based proteins, this is tricky. When we talk about animal-based proteins versus plant-based proteins, what makes animal proteins unique? First year high school biology. What is muscle comprised of? Muscles? Muscles contain muscles? What are the two molecules that make up muscle? I feel defeated. The education system has failed you all. Yes? Actin and myosin. Actin and myosin form non-covalent interactions that form the basis of the sarcomere. So this is all biology for all of you. Yes? Yeah. Yes, you've covered this in biology. There is no way you have not covered this in biology at any level. I don't believe you. You weren't there that day. Okay, so think about it. You have these two molecules, actin and myosin, they're both proteins. Proteins can interact with water, right? Because you have apolar and polar amino acids. Depending on how that protein folds, will expose different amino acids to the surface or to that aqueous phase. So if you have an animal-based protein, it is extremely good at binding water. So think about meat. Think about a steak. When you bite into that steak, it's soft, it's tender. It's what is the characteristic word to describe high-quality meat? Juicy, right? If you get a piece of meat that's really dry and tough, it's low quality. Chances are it wasn't slaughtered properly. So when we talk about plant proteins to be used as mimics or analogs for meat, how do you get that protein to arrange itself in such a way that it can bind water, that it can hold water so when you bite into it, it's juicy, right? This is a huge problem. Millions and millions and millions and millions of dollars are being spent every year by countless companies to develop an analog of meat or a petri dish that you can grow meat in so we don't have the same cost associated with meat. Now, in a communicated product, or a product where you basically mince it, it's a lot easier to do. So who here has heard of the Impossible Burger? Couple people? So the Impossible Burger is not yet approved in Canada. This is one here. So this is an Impossible Burger. I drove down to Buffalo and I bought a box. For a box of 40, it was $300. I bought it from a restaurant. You can't buy it from grocery stores, in all fairness. Now, this is a wheat protein structure. You're going to get an example of it in a couple minutes, but notice the color. How is wheat, which is not red, red? Now, let's see if, oh, I'm so sad it broke. Okay, so we'll turn this up a little bit. Test it with my hand.
Very safe.
Yeah. Do as I say, not as I do. All right, so this is the Impossible Burger. The Impossible Burger is probably the most technologically advanced. Oh, look at that. I'm over there still. Ooh. Oh, there's a big lag. That's kind of entertaining. Okay, so we have a wheat-based protein, which they call textured protein. Now, the reason they call it textured protein is because you have to do a lot of things. Okay, we can start passing them around. Perfect timing. So they texture the protein by just pass them around. Before you eat them, these, if you're gluten intolerant, don't eat them. There is gluten in them. These are a vegetarian-based, and they have a yeast extract that's GMO. So if you're anti-GMO, don't eat them as well. So I'm cranking the heat up. So the Impossible Burger, the novelty of the Impossible Burger is the appearance. So open them up and take a look at the inside of them. Take a look at the texture. One of the really interesting things about these is the color. The color of this burger is very, very unique. So when you talk, has anyone ever had the Beyond Burger at A&W? Yeah. Who likes it? This is far, far, far superior to the Beyond Burger. If you notice, the Beyond Burger has a funny aftertaste. Does anyone know why that is? What does the Beyond Burger use to make it red? Beets. So you get a really strong beet flavor after. This is really, really cool in that it genetically modifies a constituent found in soy. I'm going to play a video as this cooks.
Called Impossible.
It's turning out something that looks the future of food looks like this. If you operate what can be called impossible foods, it's turning out something that looks, feels, tastes, and smells like ground beef. Like a medium rare burger. But this patty is actually all plant, a product of genetic engineering. It's the first step in an effort to take on the multi-billion-dollar meat industry. What a big segment. It's hard to always think of the magic of a traditional burger. It tastes for one.
Okay, start watching this too. I'm going to pause this for a second. Actually, I'm going to let it play for a second, and then you'll see why.
That's the piece of iron. When you're cooking a piece of meat, what happens is the protein that's carried opens up the meat contact and catalyzes a bunch of reactions that create the volatile compounds that do that smell, that flavor, that makes meat so compelling. Your traditional veggie burger can't get the taste of the ordinary right because they ain't got that heat. But plants contain lipid molecules just like animals do. Particularly interest to impossible foods is the root of these soy plants, which contains like hemoglobin. This helps very often. It also contains that acid lean. The amount of soy roots these scientists.
So watch this. You can actually see the hamburger bleeding. So if you've ever cooked a I'm going to pause this for a second. So if you've ever cooked a veggie burger, you'll notice it's very dry. You have to put a lot of oil in the pan so it doesn't stick. What's really unique about this product comparatively to other products that are on the market is twofold. The first is the capacity of this molecule to actually bind water, and then as that protein is denaturing, that it can actually release water. So you can actually see that as it's cooking, I think I might be, there's so many left. If anyone wants another one, just keep passing them around. And then whatever they don't want, bring them back and give them out at food science. People will want them. So what's interesting, so first is the ability of that protein to bind water. That's unique in itself. The second thing that it does is when you talk about meat, when you talk about a good quality steak, you have to kill and slaughter that animal appropriately. That there. I'm going to stop this, which is swipe down to stop. I am so technologically savvy by doing this. I impress myself. I have to impress someone. So the first one, again, is the water binding. The second thing that's really interesting about this, again, is associated with the heme. So when you buy a steak, when you go into the market, you look for your highly marbled steak. What are you looking for in picking your product, your steak? What do you want to see? Marbling. So marbling is one, so the amount of fat that's mixed into that tissue. What else? Juicy. What about color? What do you look for in color when you buy a steak? Bright red. What do you avoid buying? Brown, right. What is the difference between brown, meat that looks brown, and meat that looks red? Does anyone? It's the presence of oxygen associated with that heme group. So what's unique about this product, and it's the only product on the market that actually uses it, is that it uses a plant-based heme group. So that plant-based heme is found in very, very low concentrations in the root of growing soybeans. So what they've actually done is genetically modified yeast to produce this heme-like substance that's a plant-based heme. And we'll finish watching what he has to say about it.
The yeast, and have that produce very high quantities of that heme.
When Impossible Foods has invented to be tiny, it has the foundation of a stunning imitation of a beef burger. So let's find out how they do it.
This is where we really try to understand what makes meat, test each of the kind of key parameters.
Impossible is trying to isolate and then recreate as many meat-like components as they can. And this machine is helping them do it.
So what I have in front of you is a gas chromatogram mass spectrometer. What this does is allows for us to be able to take a sample, so say a beef sample, put it in here, we'll move this sample, we have a nice little robot, they'll take this sample and move it into a cooker. So then we can cook this sample at whatever temperature we want to understand what flavors are generated upon cooking. So those aromas, again, is what creates the flavor of meat. So we will now have a fingerprint of every single aroma that is in beef. And then we can say, how close is the Impossible Burger? Where can we make improvements and iterate to identify how to make each of those particular flavor compounds? The other part that's really important is a burger for all meat is the textural component. What are the things that are driving texture in meat? Those are proteins, and we want to characterize those particular proteins. Then as we identify what those particular protein properties are, we go and look and plan for plant proteins that have those same properties. And then behind me I have Michelle, who's one of our scientists who really takes each of those individual proteins and characterizes it. Understands, is it stretchy? How much tensile strength does it have? How much water does it hold? And by characterizing each of those particular proteins, we then understand how it will behave in our particular burger.
So it all comes down to these ingredients, which include the heme, wheat protein for texture, and coconut as a stand-in for fat. Add them all together, and it starts to look more and more like a beef patty. The result is a meatless burger that's so convincing, it may as well be meat.
All right, pretty impressive.
We even asked our resident chef to give it a taste.
So it's really simulating that juicy center layer that you would get in a nice mid-layer burger. So you can see on the outside, we've got that nice
Thanks, Matt.
crust, but in the center, it's the white. Except this time, plant juice is bleeding. So let's see how it tastes.
We don't need to watch him eat it. What did you think? Did you think it tasted like meat? Yes. A little bit, eh? Like it's a pretty good, it's probably the best veggie burger on the market right now. The holdup in Canada right now is the soy lait légumes. So that GMO product right now doesn't have approval for Canada. So that's, the FDA has found no concerns with it. So it's safe to eat, but the Health Canada just hasn't caught up to the legislative requirements to allow that product on the market. So why does this happen? So, like I said a minute ago, when you add water, or a solute to water, it can actually change the volume of that water, right? So you add salt to water, and that structure changes. So when we talk about, again, that bent configuration of water, then forms that dipole moment, forming that tetrahedral structure, and that tetrahedral structure is continuous throughout as a network in water. Now, when you add an ion, that ion is a very, very highly charged molecule, and it only carries one charge. In the case of chlorine, it's negative. In the case of sodium, it's positive. So what we get is what we call clathrates. And a clathrate is the water molecules that surround that ion to neutralize its charge. So if you have a chlorine atom that's negatively charged, if you look at chlorine here, so look at the chlorine, look at where all the hydrogens are. The hydrogens all line up to neutralize that negative charge. So that molecules of water adapt a different configuration so that they can neutralize the charge of the ions. When we talk about the sodium and the plus charge of sodium, we see it here. You can see that the negatively charged oxygens align to that ion to neutralize that charge. So that's what we call a clathrate. And clathrates are referred to as bound water, meaning that water that's closely associated with that ion is no longer available to partake in a chemical reaction. What does that mean? So when you add salt into foods, it binds water, that those ions want to be dissociated from each other. Water molecules surround those ions, binding to them non-covalently. That water is no longer available to freeze. So you take water down to 0 degrees Celsius, that water doesn't freeze. That water doesn't partake in chemical reactions. So if you have a hydrolysis reaction or a oxidation reaction, this water that's bound to ions is unavailable to partake or support those chemical reactions. It is also not available to support microbial growth. This is why when we add sugars and salts, that water binds that sugar and salt. It's no longer free to support chemical reactions or support microbial growth. So we get intermediate and low moisture foods that are shelf stable because they can't support the spoilage or the growth of microorganisms. So this whole concept of water mobility, bound water, so water that's tightly associated with ions and other molecules, gives rise to this term, which we'll talk about in a minute, called fungicity. And what this is the ability of that water molecule to move from the liquid form to the gaseous form. So it's the partial pressure. You can something, you put water in it, part of that water will reach equilibrium and part of it will be in the headspace. The more ions you add, the more water is bound, the lower the partial pressure is, the lower the fungicity is, the lower is the water activity. If we can reduce the water activity, we can increase the shelf life by, one, reducing the rate of chemical reactions, but also by stop supporting microbial growth. So if water is not available to transport nutrients to those microorganisms and waste products away from that microorganism's environment will become toxic and it will die. It's not just ions that are able to bind with water. Anything that has a dipole moment, sugars, the hydroxyl group on sugars, the carboxylic acid group on acids, these aldehydes, ketones, flavors, bioactives, all of these dipole moments are able to associate with water molecules and bind water. Now, if water is bound, the definition of water that is bound is water that is unable to support chemical reactions, water that is unable to freeze at 0 degrees Celsius. Very rarely, as a food scientist, do we change the amount of bound water with the exception of adding sugars and salts. What we typically begin to modify are the other two aspects of water, which is called visceral or capillary water. Imagine within that fat matrix there's tiny pores and channels. water is associated in those very, very thin channels. That's capillary water. That water has restricted mobility, but can freeze at 0 degrees Celsius. Free water is water that you can physically squeeze out of that food. Water that's removed by drying. So think of a lemon, you squeeze that lemon, that juice is coming out, that is free water. That water is readily available to support chemical reactions and microbial growth. Fresh produce, because it has very high amounts of unbound water or free water, have very, very short shelf lives and will undergo spoilage relatively rapidly. Whoops. So when we add solutes, we can bind or change the amount of bound water. And in the case of meats, we often refer to the water holding capacity. This is of anything that's a solid-like product. So meats, gels, so jello, starch gels, gluten matrix, so bread and doughs. All of this, we talk about the water holding capacity. And this is associated with how tightly that water is associated with molecules and supramolecular structures within that food. So if you have a lot of thin channels, you have a lot of water binding. So what do you do with dough? What do? You take flour and water, you mix it together, you stir it, you just stir it a little bit, gets uniform, it's like a paste, right? Then what do? You begin to knead it. Why do you knead dough? What are you doing? You're adding oxygen, so you're oxidizing some of the proteins. What else are you doing? You're forming gluten. And what's the difference between gluten and flour? So you're mechanically kneading that dough. You're kneading that dough, you're putting in mechanical forces. Proteins are denaturing, they're unfolding, they're swelling, they're hydrating. Water is being bound to them. What is it that's unique about dough? Why can't you do it with just, let's say, rice flour? What do you need in the protein that's unique for gluten? Yeah. Yeah, so what makes it stick together? Disulfide bonds, right? So you're kneading that dough, you're mechanically disrupting it, you're putting in energy, you're unfolding those proteins, you're exposing those sulfhydryl groups. Those sulfhydryl groups can form a disulfide bond, forming a continuous network of protein, like a gel. So that water holding capacity is the ability of a network, doesn't matter what it is, if it's an ion or a solute, or if it's a gluten network, a gelatin gel, a starch paste, whatever it is, the water holding capacity refers to the ability of that network to hold water within that system. And again, this is dependent not only on the properties of the water, i.e. the dipole moment of that water, which is temperature dependent, but it also depends on the polarity and the constituents that are in the food. If it's all fat, you're not going to have a high water holding capacity. It's going to be very low. If you have a highly formed network with very thin channels, you're going to have a very high water holding capacity. This is why it's so difficult to make plant-based animal proteins. Because to mimic that structure of meat, when we talk about that structure of meat, we have the actin and myosin, and those interact by non-covalent interactions and form those sarcomeres. Those sarcomeres form bundles, and those bundles bundle to form bundles of bundles, which is the muscle. And in between all of those bundles, we have water molecules trapped within that fibril structure of that protein. So when we talk about a plant protein, that's something that's very globular, how do we get it to form or to make this kind of fibril structure? Huge challenge in the industry. Literally millions of dollars are being spent on that very question. Companies are starting to be able to do it with things like hamburger meats, but imagine if you could grow a steak in a petri dish. This is the types of technologies that are being worked on around the world, is how do you develop a protein that's not from an animal source? Typically what's being looked at are algal sources now, and some plant proteins. So how do you tell a plant protein that no, your native configuration, that globular structure is no good? You need to adapt into this fibril structure. How can I convince this globular protein to rearrange itself in such a way that it forms a fibril structure, and in doing so, increases the water holding capacity? And typically, how we do this is tremendous amounts of shear, mixing. So we put them under very, very high shear fields. So those proteins begin to align. And that alignment of proteins causes the fibril aggregation of a protein. And this way we can try to create meat mimics or alternatives to meat that have the same sensory properties. Because I can tell you, 9 chances out of 10, I'm picking a steak dinner over a plant substitute meat dinner. Again, there's a sensory perception that's very, very difficult to try to achieve. And again, there's a ton of research that's going into trying to understand how can we change the protein structure to make it mimic meat in a more closely way. Now, remember, the sarcomere, which is made up of actin and myosin, those bundles form muscles, and those bundles interact with water. So when you slaughter an animal, it's extremely important that that muscle is not stressed, or that animal is not stressed. So if that animal knows what's coming, and it knows where it's going to be in a couple minutes, it's going to be in hamburger patties, it's going to be low quality meat. Because that stress causes what? What happens when you're stressed? What happens when your muscles are tense or you've done aerobic activity? What do you produce? Lactic acid. Lactic acid changes the pH, and we'll talk about what that does to proteins, but one of the things it does is it changes the solubility of that protein. By changing the solubility of the protein, you change the water holding capacity of that protein. So now that animal's stressed, the pH isn't right, all of a sudden now those proteins don't hold water, and now we get a defect in pork known as pale, soft, and exudative. Meaning, when you take that pork chop out of its package, that piece of, I don't even know what it is, and I should, but that piece of absorbent pad that's underneath is saturated with water, and it's very, very mushy. On the other extreme, we can have dark, firm, and dry. So if the pH is on the other extreme, we can have it being very, very dry and chewy. So again, imagine the slaughter of an animal. How you slaughter an animal determines the pH of the muscle, which determines how that protein is going to interact with water and is going to affect the overall juiciness of that steak. So if you work in an abattoir that doesn't undergo good slaughter practices, you're going to produce low quality meat. So there's a whole area of animal welfare that deals with trying to minimize defects associated with improper slaughter. We also have 2 world-renowned meat scientists. The first is Dr. Shai Barboot. Dr. Barboot is an expert in poultry, specifically meats, and Ben Borer is specifically an expert in pork processing. If you're interested in the animal protein industry, Shai Barboot has actually written an entire textbook that is freely available. You can download it. It's an excellent resource if you're thinking about going into anything associated with animal husbandry or animal manufacturing. It gives you the characteristics that you should be looking for when you're designing a high quality meat product. So again, when we talk about the biological functions of water, one of the biological functions, or one of the prerequisites for good quality food, is that water associating with other constituents, either sugar, salts, whatever it may be. So biological tissues, muscle. In plants, the turgor. So if you leave celery in your fridge for a long time, it becomes limp, right? What do you do to get it so it's not limp anymore? You put it into a glass of water. So water plays an extremely important role when we determine the sensory properties of any food. Doesn't matter what it is. Good quality food has good water binding properties. This is associated, like with what we just talked about, the Impossible Burger. But from a nutrition perspective, just think about the importance of sugar and salt in the human body. Without water, they could not perform their physiological functions. They would be immobilized within your tissues. You wouldn't be able to transport them through the circulatory system. The ability of water to interact with sugar and salt, again, is associated with that bent structure of water, that dipole moment, which then can hydrate or form a clathrate around that molecule, which then allows it to be solubilized in a continuous phase of water, which then allows your circulatory system to move salts and sugars throughout your body, which again is of central importance. When we talk about sugar, we talk about electron transport. When we talk about salt, we've already talked about the importance of sodium in ion or protein pumps. So moving bioactives or moving food metabolites across cellular membranes. We require sodium to do that, and potassium for muscle contractions. So we have to be able to move those molecules with ease through the human body. And again, it's water that does that. But water goes beyond just moving solutes. It's essential in chemical reactions where we have a hydrolysis. So when we have a hydrolysis, it requires one molecule of water for every molecule we hydrolyze, or every bond we break. So when we talk about protein metabolism, carbohydrate metabolism, lipid metabolism, all three of those require the presence of water to undergo that chemical reaction. If you are a dehydrated state, these reactions become less effective because you don't have water available to associate with these breaking of bonds. So we need it for nutrient transport. We also need it for lubricity. So your tears, your saliva, the formation of your bolus is all dependent on water. We also have, again, the metabolism. The other aspect that it's very important for, again, is heat loss. So regulating body temperature. When we talk about foods, the ability of that molecular mobility of water is a determinant, is the primary determinant on whether or not you are going to have a shelf-stable product. What is the water activity associated with your food? Water activity, again, is not just dependent on the absolute amount of water that is in that food, because water can form collaterase with other molecules. So if you add sugar or salt, the water content stays the same. The water activity drops because, again, it is bound. It is unavailable to partake in chemical reactions. It supports enzymatic reactions. One, in that it requires water to undergo hydrolysis, but also we have to transport the substrates to the face of the enzymes. So any chemical reaction requires the solubilization of whatever constituents undergo that chemical reaction into that same aqueous phase. So water activity is probably, if you take one thing from this course in the food science aspect, it's the importance of water activity. When we talk about water activity, again, for the 10th time, it determines the ability of microorganisms to grow. So if you're below 0.9, we don't see microbial spoilage. Below 0.8, we don't see yeast spoilage. Below 0.7, we don't see mold spoilage. But it's also essential when we talk about the structure of foods. Think about a dried pasta. The brittleness, the hardness of that dried pasta. The flowability of a powder. So skim milk powder if you're a weightlifter, or if you're a fitness guru that takes supplements. All of those types of powders are always used in the food industry as starches, as flours, as proteins that we incorporate into processed foods. So the ability of a molecule to bind water is of essential importance in determining not only the shelf life of that food product, but also the organoleptic sensory properties of that food. How crunchy is it? How brittle is it? How is it going to rehydrate when you expose it to water? So your instant coffee or your skim milk powder, do you have to heat up that water to get that protein powder into water? Or can you just put it into a water bottle and shake it after the gym? We have to design and engineer those proteins so that they can very quickly and rapidly absorb water. So next day we'll pick up again at the concept of water activity and the importance of food science.